Damn, I gotta give him this guy again. Just come up with something.
I'm not gonna leave yet. I'm not leave yet.
Okay, welcome back. We're going to jump right into it, chapter 4. And I'll give back your test and quizzes at the end of class. I want to make sure I finish this. Yeah, in general, the second test was a lot better. Like, people did a lot better on average, so I'm happy about that. That's good.
There's all those threats about being beaten.
I'm one of them. I'm gonna be one of them.
I do not recall making such threats. The recollection
The
of
camera.
events-
The camera.
We have it on tape.
I am very.
He had amnesia during the segment.
So now we're going to jump into chapter 4, where we're going to talk about higher order linear differential equations. Basically, Alright, so we know how to deal with first order, and we know how to deal with second order. That was what chapter 3 was about. Now we're going to deal with pretty much every other order above that. It's called higher order differential equations, which I might abbreviate bold if I don't want to always write that. So bolds, yes. The theory is very similar to the theory for second order differential equations, so I don't really want to go into that too much. I'll probably just list some facts here for you to just be aware of, and then we're just going to jump right into doing some problems. So let's just let's start there. So if you paid attention when we're talking about second order linear differential equations, you'll fit right in here. Higher order. That's just only of order n. Right. So I'm just going to give you the general form, the standard form. This is y to the nth derivative. Remember, when you put things in a power in brackets like that, it means the derivative. So this is the nth derivative plus p1 of t times y to the n minus 1 plus p2 of t times y to the n minus 2. Goes all the way down to pn minus 1 of t times y prime plus p n of t y equals g of t. And similarly, if g of t equals 0 for all t, so it's called homogeneous. And a lot of things that we expect to have from second order differential equations we also have here. So for example, we have an existence and uniqueness there. Right, so that is if all the p functions are continuous, we are guaranteed have a unique solution. Call this equation 1. Right, so we also have an existence and uniqueness there. Once all our coefficients are continuous functions, if the p's and the g are continuous, we have existence and uniqueness. Solutions, all solutions. come out in this case. The nice case is what we're dealing with, when everything is continuous and everything is nice. In this case, every solution can be written in the form y is equal to c1 y1 plus c2 y2 plus cn yn, where y1 up to yn are solutions to 1, and the Wronskian of all of these guys. Defined similarly, right? So you have y1 prime, all the way down to y derivatives, all the way over here to yn prime, all the way down to yn. So the Wronskian is similar, it's just a determinant, and in the case where these guys are continuous, we are guaranteed to be able to find a solution such that we can write it in this, or all these guys' solution, and the Wronskian equal to 0, which means that the y's are linearly independent. In other words, an nth order differential equation will have n linearly independent solutions once we have continuous coefficients. Right? It looks just like a second order, except you extend it to n terms. Basically, a lot of higher order is going to be like this. Things that used to work for 2 will now work for n things, right? But it'll generalize pretty naturally, pretty much the ways you expect. There are some differences in applications and things like that, but it's not in our syllabus to cover those things. So things will be pretty much as you expect. What else did I want to tell you? So when all the coefficients are continuous, we're guaranteed to have a unique solution of that form where they're all linearly independent, and we can find the coefficients to satisfy any set of initial conditions that we're given. And of course here, we have to be given them up to the n minus first derivative. So in this case, we can always find a solution that will fit any set of initial conditions, guaranteed. Right? Once our coefficients are continuous. Anything else I wanted to tell you? We have a generalized Abel's theorem. Right, which it says, if everyone's continuous and blah, 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 the Wronskian of all our y's can be written as a constant times e to the integral of minus p1 of t. Right? Remember, p1 is the coefficient of the first derivative, of the second to highest derivative. Right? That's this guy. Right? So Abel's theorem actually works in the nth order case, and that's how you find the Wronskian. We also have a generalized variation of parameters, all that. So this is what P is equal to y1 times w1 over w plus y2 times w2 over w.
Is it positive y1 or negative y1?
If you memorize the formula this way, in which I'm going to tell you, it's always positive. the thing is, W1 will usually have a negative sign, right? Because remember, the signs alternate. So this might give you a negative, positive, negative, etc. This comes from the Laplace expansion of the determinant. Okay, so where Wi is so the usual Taylor-Wronskian, replace for the y1, replace the first column with this. For y2, replace the second column with that. y3, replace the third column with that, etc. And you find the determinant of that. You do this division, you plug into the formula, and it will give you the particular solution. Technically, this isn't in our syllabus. It's in section 4.4, which we're not going to cover, but I thought I'd tell you about it anyway. And I also gave an extra credit homework problem, a homework set on 4.4, so you can try it if you want to, but it's completely optional. But I just thought I'd tell you, this thing works in general. It's pretty nice to know that that works in general. Okay, those are all the facts I sort of want to tell you. For now, we will focus on, well, in general, the only thing we take from chapter 4 is the constant coefficients case. So this is pretty much all we need to know in this course. This is what our syllabus will cover. So we're going to talk about higher order differential equations, solving the ones with constant coefficients, both homogeneous and non-homogeneous. For the non-homogeneous case, we'll only look at undetermined coefficients. Yeah, so we're not doing variation parameters, but I just want you to know it can be done. We're only going to look at the cases where we can use undetermined coefficients. The idea is the same. For second order differential equations with constant coefficients, how do we solve them? What was our technique?
Get the characteristic equation.
How? What did you have to assume to get the characteristic equation?
We assume that the solution takes the form of a e to dx, or
e to the RT, right? We obtain a characteristic equation which is now an nth order polynomial, nth degree polynomial. Right, so the idea is we start out the same. The difference is now we don't get a quadratic anymore. We get an nth degree polynomial. So if we're looking at a third order differential equation, we'll get a cubic. Looking at a fourth order differential equation, we'll get a quartic. If we look at a fifth order, we'll get a quintic, and so on and so forth. So this is why I sent you that email about looking at how to solve all these various kinds of polynomials, because we're going to need to be able to do that. And yeah, they don't hold anything back here. Pretty much everything you need to know learned about solving polynomials back in pre-calc and all that, they expect you to remember everything. Long division, synthetic division, rational roots theorem, sum of cubes, difference of squares, all that stuff, factor by grouping, all that stuff where you learn about polynomials, you're expected to know it here, right? So,
I'm gonna go back to high school.
to go at high school. So, let's actually just get. Okay, let's jump. Jump off the cliff. Right. So there are several cases you can encounter, right? Let's talk about the first case, factoring. By thinking of the tri-equation as a lower degree. This is one case that you might end up with, and there was a problem on the bonus problem for the second test that you needed to do this for. So what's an example of something like that? Let's say I needed to find the general solution to this equation. What is the characteristic equation for this? R to the fourth minus 2r squared just 3 equals 0, right? So now this is a fourth degree polynomial. The trick is we want to factor this, hopefully, so we can solve it. But we can think of it as a lower degree polynomial. What do I mean by that? Well, it's quadratic, right? It's fourth degree, but it's sort of quadratic. You sort of can think of this as it's quadratic in r squared. Right? So it's like I have something squared plus a constant times something plus a constant, right? So it's a fourth degree, but technically I can think of it as a quadratic. That's sort of what I mean. So there are times when you'll see this, it's a higher order thing, but if there'll be some sort of pattern with the powers, then you can think of it as a lower degree polynomial and use what you know about that. So now if we're thinking of this as a quadratic, how can we factor it?
R squared times
R squared, R squared,
3 and 1. Negative 3 plus 1.
minus 3 plus 1. That works, right? So then I get r squared is equal to 3. Or I get r squared is equal to minus 1. So in this case, r is equal to plus or minus radical 3. In this case, r is equal to plus or minus I. Right? So what does the general solution for this look like?
Y is equal to C1. E to the square root of 3t plus C2. E to the negative root of 3t plus C3 cosine t plus C4 sine t.
Right? So now we had a fourth order differential equation, which means you should have 4 solutions in your answer. Right? This was a bonus, so technically you didn't know this at the time I asked it, but on the test, when I asked the bonus, a lot of people, they saw like a fourth order, a sixth order, but they only gave me like 2 solutions. Like you have to have as many solutions as the highest derivative, right? So that's one thing you have to keep in mind. Okay? Right. So any questions on that? That's one of the easier cases. Another case, special factor. Special factoring is what they call things like factoring by grouping, difference of squares, sum or difference of cubes, etc. It's another case that you might encounter. Let's do some examples of that. That's the first one.
What?
What?
That's why I said what.
What is this?
R cubed.
R cubed plus what?
R cubed plus 1 equals 0. How do I do that?
R cubed is equal to -1.
R cubed equals to what?
Can we use the formula for that? The cube formula?
What is the formula?
R plus 1. R plus 1.
Right, there's a formula. This would use the sum of two cubes, right? A cubed plus B cubed is equal to A plus B, A squared minus AB plus B squared. Right? Now, if you just solve this as R cubed equal to
No.
-1, you take the cube root, you just get -1. That's only one solution, which is not good enough. And it's not like it's a repeated root or anything, so that wouldn't work. You'd miss some guys. So the trick is to factor it using the sum of two cubes formula, because 1 is actually 1 cubed. Right? So you have R cubed plus 1, that's just R plus 1 times R squared minus R plus 1. So from this guy, you get R equals -1. You set that equal to 0. From this guy, you can't factor it, so you use quadratic formula. R is equal to minus B plus or minus square root of B squared minus 4AC over 2A. So this is just 1/2 plus or minus radical 3 over 2I. So the solution is
C1 e to the negative t plus C2 e to the 2 over t cosine squared e to the 3 over 2t plus C3 e to the t over 2 cosine squared over 2t.
right, and we have 1, 2, 3 linearly independent solutions for a third order differential equation. So that's everybody. I'm actually going to show you another way to do this later on. But yeah, if you see something like this, sum of two cubes. This one, y to the fourth derivative minus 16y 0.
All to the 4 minus 16.
Right? Characteristic equation here, y to the fourth minus 16 equals 0.
R squared plus 4, R squared minus 4.
Right, it's actually the difference of squares. Okay, what does that mean?
You can still factor the R squared minus 4.
Yeah, we can do that. So it's r minus 2, r plus 2,
And then R squared plus 4.
r squared plus 4 equals 0.
Two.
So what are the solutions?
2
r
negative
equals
2.
2, r equals minus 2,
And plus or minus 2i.
r equals plus or minus 2i. Right? Which means our general solution is c1 e to the 2t plus c2 e to the minus 2t plus
C3.
c3 cosine 2t plus c4 sine 2t. We have 4 linearly independent solutions because we have a 4th order differential equation. And the trick here was thinking of this as the difference of squares. Okay. What about this one? Factor by grouping, right? You have 4 terms, no common factor really. So factor by grouping is one of the first things you think about. This gives us r cubed minus 2r squared minus r plus 2 equals 0. How do we do factor by grouping?
We factor out an r squared from the first 2 terms,
R squared is common in the first 2.
and we could factor out a -1.
Factor out a -1 from the last 2. Now r minus 2 is a common factor. We can factor that out. And we'd be left with r squared minus 1. So this gives us r minus 2, r minus 1, r plus 1, because that's the difference of squares. So we get r equals 2, r equals 1, r equals minus 1, which means our general solution is c1 e to the 2t plus c2 e to the t plus c3 e to the minus t.
But not every time we have 4 terms, factor by grouping is gonna work, right?
Not every time, no. In fact, later I'll give you 2 examples from now. We're going to have one where it's not going to work. Is everyone with me so far, right? I mean, conceptually it's not a big jump. It's just you have to remember how to deal with all this algebra. Another case you can, it comes in handy a lot of the times, is reversing a binomial expansion. There are a couple ways you can think of this. Just to remind you, remember something called Pascal's triangle?
Nope.
No. He's like, oh yeah, tell me now.
Alright, it starts with a triangle of ones, right?
Then you have
You put a 1, and you keep adding each one in between to get the other one. So 1, add these 2, you get 3, add these 2, you get 3, 1, 1, add these 2, you get 4, add these 2, you get 6, add these 2, you get 4, 1, etc. Right. Now what these guys actually do is they tell you the coefficients of a binomial expansion to the power that's on this level. So example, this tells us that if I have, let's look at this one, a plus b squared, then the coefficients would be 1a squared plus 2ab plus 1b squared, right? See, the coefficients come from the triangle, right? So if you had something like a plus b cubed, you have 1a cubed plus 3a squared b plus 3ab squared plus 1b cubed, right? So you have the 1, 3, 3, 1, which comes from this triangle, right? And how it works with the powers is you start with the highest power on one of the variables and you count the powers down, right? So a cubed, a squared, a, no a, right? The other one you go in the opposite direction. So b cubed, b squared, b, no b, right? And the coefficients will take on the numbers according to this triangle, right? There is another way to think of it, but it has combinations in it. If you don't know, if you haven't taken like combinatorics or probability, you probably won't see that, so I won't tell you about that. But this is the idea, right? So basically this is a pattern that you can look for. Whenever you see the coefficients sort of have this pattern, you can sort of factor by going backwards. So for example, that y triple prime minus 3y the equation here would be r cubed minus 3r squared plus 3r minus 1. In a weird way, you could also do this by factor by grouping, but you sort of have to rearrange. It will be weird. If you want to apply the factor by grouping, what you do is you group these two, and then you factor it by the difference of cubes. You get a common r minus 1. You can try it if you want, but I really want to emphasize this method. So the idea is here, I look at this and I'm like, 1, 3, 3, 1. Right? Which sort of it's probably a cubed of something. Now the signs alternate, but that could be just putting a minus in here, right?
Yeah.
Because that would give us 1a cubed plus 3a squared times minus b plus 3a times minus b squared plus minus b cubed, right? And that will actually alternate the signs for us. So this I could actually think of, oh, that is just r minus 1 all cubed. Right? Just by noticing that pattern, because you should be familiar with this triangle.
Okay,
Yeah.
What would you be looking for to solve, like to figure out what b is? Like here it's 1, so it's like kind of obvious, but in general, like how would you, like what are you looking for?
Oh, this pattern.
So I'm saying, so you know it's like Pascal's triangle, you see 1, 3, 3, 1, 5, then like how do you figure out what b is in that? Here it works out kind of nice, like this b is negative 1, so
Yeah.
or let's say b is equal to 3, where you're like multiplying something.
Well, you could also, so let's say it was something like, let me just finish this first and then I talk about the other one. Give you another example. So of course this would be r is equal to 1, but this in case is a repeated root, right? So it's r1, 2, 3 is equal to 1, right? So what would the solution look like here?
C1 e to the t,
C1 e to the t,
C2 t e to the t,
C2 t e to the t, plus C3
t squared.
t squared e to the t. Right, that would be the general solution. Yeah. To be fair, it's not always as obvious with these. Like, so for example, but the idea is you should always be able to factor out constant coefficients that it gives it that pattern. So let's say I had triple prime minus So let's say you see something like that.
R minus 2 cubed.
So the idea is you have this r cubed minus 6r squared plus 12r minus 8 equals 0. The idea though is you can think of this as a 3 times 2r squared plus a 3 times 4r minus a 1 times 2 cubed. Right, so the idea is you should be able to factor out the coefficients to get that pattern, right? It's something you'll see easier with a lot of practice. It's not. It might not be obvious to you, like I wouldn't see that, but if you have enough practice, you'll see it, right? It's going to be one of the things you look for when you start racking your brain. Well, factor by grouping doesn't work. This doesn't work. You'd start to think of that as one of them, and then you try to figure out to make the coefficients work, right? So there are a few things that will go through your head. If I'm giving something with 4 terms, the first thing I look for is factor by grouping. So if I realize that doesn't work, then I'll try something else. I'll probably look at this second, right? And then I try to see, can I actually work out the coefficients so that I can get these guys to work out? And then if that doesn't work, I would try what we're going to talk about now. Alright, so as with anything, there are a bunch of methods that you know, but you sort of try to get the easiest ones out of the way first. And, right, yeah, so basically this was r minus 2. Try to get the easiest ones out of the way first, and then you keep working your way down. So another situation you might end up in is one where you have to do long or synthetic division. With the rational roots theorem, because 391, they're not going to tell you what one of the factors are. So you'll also have to know the rational roots theorem. Does anyone know what the rational roots theorem says?
The last coefficient, the constant divided by the first coefficient.
Right, so if you have like a general polynomial, an x to the n plus an minus 1 x to the n minus 1 plus dot 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 all the way down a1x plus a0 equals 0. Now the idea is if you want to see if something is a factor, the rational roots theorem says you don't have to have a rational root, but if one exists, it should take on a certain form. If a rational root exists, it will, rational just means fraction, right? A ratio of integers. It will have the form plus or minus a factor of a0 divided by a factor of an. Right, so random example. We'll just make something up.
That takes more time.
Not necessarily, no. Not if you sort of know what you're doing. If it does work, you should be able to see it spotted quickly. Right, so something like this. I don't know if there's a solution to this that's rational, but if one exists, right? If a rational solution exists, and I'll just check them to make sure. It must be, well, what are the factors of 4? 1, 2, 4, right? What are the factors of 3? 1 and 3. Which means if a fractional solution exists to this, it must look like it should either be plus or minus 1, plus or minus 1 over 3, plus or minus 2, plus or minus 2 over 3, plus or minus 4, plus or minus 4 over 3. Right? It has to be one of those, if it exists. It doesn't have to exist, but if it does, it's going to be one of these guys. Right? And all you have to do is you plug in and try to check them. Right? So let's actually sort of use this theorem with long division or synthetic division. I sort of prefer long division. But if you know synthetic division, you can use it. It's just a force of habit is to do long division only. Example. Y triple prime minus 3y double prime. Y prime. Okay, so you sort of look at that, and factoring by grouping wouldn't work. And it's not a binomial expansion, right? There's no way to get the coefficients to look like anything in Pascal's triangle. So then I would think of this, right? So I'm hoping that there's a nice solution to this, as in it takes on the form of a fraction. But what are the possible candidates? Well, it would be plus or minus 1 or plus or minus 5. right? Those are the possible candidates I would look at, right? So let's start with an easy one, right? Try to find an easier one out of all those numbers that you think would work. Try 1. 5 is a big number, right? You start with the smaller ones, right? -1 actually works. If you plug in, so I have r cubed minus 3r squared plus r plus 5 equals 0. Now if I plug in r equals -1, what would happen? -1, -3, -1, that gives me -5, plus 5, that actually gives me 0, right? So try r equals -1, and it works, right? And you'd know to try that because the possible candidates were possible candidates were plus or minus 1, plus or minus 5. I just picked one of the easy ones, right? I could clearly see that plugging in a +1 just wouldn't work. You can look at that pretty quickly and see. Try the -1, and it works, right? So once you find one that works, now you're going to have to figure out how to factor that out. And this is where the long division comes in. So the rational roots theorem starts you off by getting you something that works. If r equal 1 is a root, what does that mean a factor had to be? R plus 1 had to be a factor. Right? If plugging in r equals -1 makes it 0, it means when you factor it, there's going to be someone that looks like this. That's where you get the r minus 1, right? So what does that mean? Divide. So now we're going to have to remember our long division. So we have r plus 1, and I want to divide it into r cubed minus 3r squared plus r plus 5. Right? It's very important that you account for all the powers, right? So if there, for example, was no r, you put 0r. It's things have to line up, right? So you write down all the powers for the whole polynomial. Right? And here's how we do the long division, right? You take the first guy here, divide into the first guy here. R into r cubed goes r squared. They're going to take this, multiply everyone here. R squared times this, r cubed, r squared times this, r squared. Subtract this from the line above. Right? That dies. Minus 3r squared minus r squared gives me minus 4r squared. And then I do it again. R into this, minus 4r. Take minus 4r, multiply everyone here. Subtract it from the line above. So plus r plus 4r gives me 5r. Keep doing it. R into this, plus 5 times this, 5r, 5 times 1, plus 5. I'm going to add this 5, minus 5 gives me 0, right? And you should get 0. It should be no remainder because the thing is a factor, right? It means it divides into it evenly. There's no remainder when you're left over. So if you're sure r plus 1 is a factor, you should get 0 here. But that means you could actually factor that. This means this r cubed minus 3r squared plus r plus 5 is actually equal to r plus 1 times this guy. Can we factor this?
No.
No, right? So here we get r equals minus 1. Here we use quadratic formula. Minus b plus or minus the square root of b squared minus 4ac all over 2a. And 2 plus or minus. Yeah, because this becomes 4. So 2 plus or minus I, which means our solution is c1 e to the minus t plus c2 e to the 2t cosine t plus c3 e to the 2t sine t. So that's another case. All right, so you might get a polynomial. It looks sort of ugly, but you can try something like this. The rational roots theorem, try to break it down and do a long division or synthetic division if you prefer. Sort of partial to long division, fond memories from childhood. Now, the last case we're going to talk about is one you probably haven't seen. I mean, even if you've done complex numbers in high school, you probably didn't see this. Maybe you did. But this is probably new, so I put a bunch of examples on this one. The last case you'd notice is the roots of unity. Polar forms. I'm not really going to go into that dimension of it. You're sort of going to need to apply Euler's formula in a weird way, but roots of unity. So, for example, if this is similar for complex numbers. So if z is a complex number, the solution to z to the n plus 1 equals 0. No, equals 1. And the solutions are called the roots of unity. Right? These are the roots that give you 1, right? So 1 is the unit. It's called the roots of unity. Right? So how do we deal with those? Well, I don't want to tell you about that. Trick. Any complex number, you can write it in this form, right? It's called the polar form of the complex number because it sort of comes from the r and the theta are the same r and the theta you get from polar coordinates, right? The idea is any complex number, you can plot it on the real and imaginary axis. So you'd have a point called a comma b, this is called an Argand diagram. If you can tell me what the r is and the theta is, I can locate that point just as how I can locate a and b. Right? So it's the same sort of polar form. It's called a polar form because you use polar coordinates together. Right? So the r is going to be the radical of a squared plus b squared, blah, blah, blah. Right? You don't have to look into that too much. The important idea is this fact, that I can write any number to look like this. In particular, I can write 1 to look like that. How do I write 1 as the polar form? How about minus 1? Because this one is the famous one. E to the I pi. Right? When I introduced Euler's formula, that was the first equation I told you about, which is the coolest equation in all of math, right? However, because it's a polar form, right? we can write a sine as cosine, which means it repeats every 2 pi. So I can actually write 1 as this, right? I can write minus 1, I can write like that. Positive 1, it's e to the I 2 pi, but it repeats every 2 pi, so I can write that. For your information, you can write this as pi over 2 plus 2n pi. Though we're not going to use that one often. This happens if you have complex coefficients, right? Minus I you could write as e to the I 3 pi over 2 plus 2n pi. Right? And this is because you know e to the I theta is cosine theta plus I sine theta. Right? So the idea is we can write things to look like this, and that can actually help us to solve these equations in a pretty sophisticated way. So let's actually do an example. So let's redo this one. I don't need to show you. So we've seen this before. If I saw this, I'd use the sum of cubes form. But let's say for some reason you blanked out on that, right? But I don't know. I suppose it can happen. So you'd write this as this, right? And now the idea is this looks like something to the n power equals a unit, right? So how do you get to that? Well, you have to rewrite the unit like this, right? It's one of the easiest ways to get to the answer. So this would mean I can take r cubed equals, instead of minus 1, let's write it to look like this. Seems to make it more complicated, but it actually doesn't. It actually helps us to solve it. Right? So this means r would be what? Well, I'll just say the cube root of both sides, but that just means dividing the power by 3. And remember, this will work for every integer n, but obviously things repeat after a while. It turns out you only have to do 0, 1, 2. You always only have to go up to the n minus first power. Beyond this, it will just repeat. So for the third order, you only need 3 solutions, right? And it actually start repeating after that. So you always have n goes from 0, 1, all up to the n minus 1. For a kth order. So let's look at the solutions to this and see if they actually agree with what we had last time. This would mean that R1 is equal to, well, plug in n equals 0, right? E to the I pi over 3, if n is 0. But that's what? Cosine pi over 3 plus I sine pi over 3. Right? Right? What's cosine pi over 3? Well, don't all shout at me
What now?
What's
It's like
sine of pi over 3?
Root 3 over 2.
Radical 3 over 2. Okay. Now let's go to R2. This means e to the I, plug in n equals 1. If n equals 1, I get pi plus 2 pi. That gives me 3 pi over 3. That's just e to the I pi, which I know is minus 1. R3. I'm going to show you a trick how you could have gotten rid of this if we have something bigger in the bit. If n equals 2, plug in 2 here, I get 4, plus this I get 5, so this is e to the I 5 pi over 3. Right? 5 pi over 3 is in the fourth quadrant, which means the cosine is positive 5. So this just gives you the same thing as cosine pi over 3, it's positive. But the sign is negative, so this will give you a minus I radical of 3 over 2. So R1 is equal to minus 1, and R2 and 3 are equals to 1/2 plus or minus I radical of 3 over 2. And if you look at what we did last time, those were the answers we got. Right? So this is y equals c1 e to the minus t plus c2 e to the t over 2 cosine radical 3 over 2t plus c3 e to the t over 2 sine radical 3 over 2t. So that was just to illustrate the idea. Of course, if I had this, I wouldn't have done this. I would have just did the sum of two cubes and got to the answer quicker. But there are times when you don't have a nice formula where this will work. So let's do another example. This gives us r to the fourth plus 1 equals 0. Now we don't have a nice formula for that. Right? But the idea is I can write this, bring this guy to the other side and think of it as a root of unity. This would mean r to the fourth is equal to e to the I pi plus 2n pi. This would mean r is equal to e to the I pi plus 2n pi over 4. And I take n to be 0, 1, 2, 3. So let's do the first solution. When n is 0, what do I have? So the first solution I get when n equals 0, I get e to the I pi over 4. That's just cosine pi over 4 plus I sine pi over 4. That's just radical 2 over 2 plus I radical 2 over 2. Okay. R2, this is when n equals 1. I would have e to the I, if I put in n equals 1, 3 pi over 4. So this would give me cosine 3 pi over 4 plus I sine 3 pi over 4. 3 pi over 4 is in the second quadrant, means the cosine is negative. The sine is still positive. Now, here's a trick. You can actually stop here, because you actually, at this point, you'll actually know what the other two solutions are. Right? Well, it's sort of a theorem. I'm not going to prove it, I can just tell you. Complex roots always come in conjugate pairs. Always. I.e., if a plus ib solves a polynomial, so will a minus ib. These guys are called conjugates, right? When you change the sign of the imaginary part, you get what's called a conjugate. Now, if one of these is a solution, the other one is automatically a solution. You don't even have to check it, right? So if I'm looking at these, if I know that radical 2 plus I radical 2 over 2 is a solution, it means if I put a minus sign here, it's again a solution. If this is a solution, if I put a minus sign here, it's again a solution. I only need 4 solutions. So once I have 2, and I know I can automatically get another 2, I don't need to go through and figure this out. I just know changing the signs here will give me the other 2. Right? So my R3 is going to be radical 2 over 2 minus I radical 2 over 2, and my R4 is going to be minus radical 2 over 2 minus I radical 2 over 2. I can just stop there, because I know complex roots have to come in pairs. Right? So once I find one, I know another one right off the bat. This can cut down the work that you have to do in a lot of cases. And you can go back and see in this one where I did the R cubed plus 1, when I got a complex number and I got minus 1, I automatically know that the conjugate of the first one I got would be the other solution. I could have not have to work that out. I'm going to do another example where we see this idea being applied. So this means the solutions are radical 2 over 2 plus or minus I radical 2 over 2. R3 and 4 are minus radical 2 over 2 plus or minus I radical 2 over 2. C1b to the radical 2 over 2t cosine radical 2 over 2t plus C2b to the radical 2 over 2t sine radical 2 over 2t plus C3e to the minus radical 2 over 2t cosine radical 2 over 2t plus C4e to the minus radical 2 over 2t sine radical 2 over 2t. That's the solution, the general solution. Now you might be wondering why you don't put negatives in the angles. It's because it doesn't matter, right? Cosine is an even function, so if I put a negative in the angle, it doesn't matter. I can write it as positive. Sine is an odd function, so if I put a negative in an angle, I can actually just factor the negative out, even though technically that's not what I'm doing, so it will still look like this. Can I get rid of this? That one you do it that way, because you don't know a nice formula to factor this. By the way, if this was a minus one, I could do a nice formula to factor this, but maybe I'll talk about that next time. So what would we have here? So my first solution would be what? E to the I pi over 6, right? Which is cosine pi over 6 plus I sine pi over 6. Cosine pi over 6 is radical 3 over 2. Sine pi over 6 is a half. My second solution would be e to the I 3 pi over 6. This gives us what? Pi over 2. Right? Which, we actually know that one. That's just I. 3. This means I plug in n equals 2. This is going to be e to the I 5 pi over 6. This gives me cosine of 5 pi over 6 plus I sine of 5 pi over 6. 5 pi over 6 is in the second quadrant. The cosine is negative, while the sine is positive. Now remember what we said, complex roots come in conjugate pairs. If this works with a plus sign, it will also work with a minus sign, so that gives me another solution. This works with a plus I, it will also work with a minus I, that gives me another solution. This works with a plus, it would also work with a minus, that gives me another solution. So I have 3 solutions, but they come in pairs, so I automatically know the other 3. R4 would be radical 3 over 2 minus radical 1 over 2. R5 would just be minus I. R6 would be minus radical 3 over 2 minus I 1 over 2, since complex roots come in conjugate pairs. So once I realize I have 3, I automatically have 3 more, and all I need is 6 because I have a 6th order, so I can just stop after doing 3.
What if I have 2 complex and another like integer or something? Can I assume 2 other solutions?
No, it doesn't work with real numbers. It works with complex numbers. It has to have an imaginary part for that trick to work. It doesn't work with real numbers. Like, for example, think of x plus 1 equals 0. X equals minus 1 work, but positive 1 doesn't.
No, what I meant, if let's say I have 3 solutions, but 2 of them are complex numbers, and a third one is an integer, for example. Could that happen?
Oh, that would mean you have a 5th degree. You have a 5th order. That could work with a 5th order. So we can have y is equal to c1 cosine plus c2 sine plus c3 radical 3 over e to the radical 3 over 2t cosine t over 2 plus c4 e to the radical 3 over 2t sine t over 2. And we have 6 solutions because we have 6. It's a 6th order ODE. I had 2 more examples, but we're actually out of time. I wanted to do a non-homogeneous one. But as far as the concepts go, I've taught you everything you need to know. It's just a matter of dealing with variations here. So you can try the homework if you want, but I'll do the last 2 examples next time.
One more question. The only happens when you call a negative R. When it starts with, like, let's say R6 equals negative 1 or plus 1, right?
No, like next time I'll give you some examples where it's not necessarily a 1. The idea is if it's something else, you can factor it out. So if I have something like r to the 6 plus 5 equals 0, I could just think of this as r to the 6 equals 5 times minus 1. And so my r would be the 6th root of 5 times e to the I plus 2 over 6. So I could do something like that. So all my solutions get multiplied by 6th root of the coefficient. All right, I have stuff to give back.